Hello, I'm Nadir Mahammed from École Supérieure Informatique Sidi Blablas. I'm really happy to be with you today. I will present to you our work. As you can guess from the title, we are working on business process optimization and evolutionary algorithms. So before we dive in, let's see what's a business process. Here's a business process. As you can see, it can be defined as an oriented and evaluated graph where the nodes are tasks and edges the resource consumed or used by these tasks. When a business process where each task component can be executed by one or more services, it's called a business process design. And here's why. So, how to represent a business process design? We propose to represent it using a task matrix. This matrix contains the relationship between the different tasks composing a business process design. So, what are we really working on? Today, I will present to you an approach to optimize the generation of these business process design by focusing on their tasks, resources, and attributes. To get there, we use an enhanced algebraic algorithm that we will talk about it later. Okay, we talk about business process. Let's take a look to the optimization problem. More formally, the problem of business process optimization that we are dealing with can be defined as shown on the present slide. As you can see, using a set constraint, which means that we are dealing with a multi-objective optimization of business process design. So, let's take a closer look at the genetic algorithm. We propose the MP and SGA2, which is a modified version of the canonical and SGA2. We propose to add the multiple subpopulations feature to it, and this is how it works. First, an initial population is generated randomly. Then the crowding distance, sorting operator is applied on it. After that, a number of subpopulations is generated. Thereafter, the NSGA2 is applied on each subpopulation for a defined number of iterations, which means that we are applying the NSGA2 into the NSGA2. After that, we unified the subpopulations to form the next initial population. I explain briefly. Each subpopulation is sorted regarding to their fitness function. The best or elite of each population migrates to form a new population. Maybe a few words about the stopping criteria. Many stopping criteria can be used. For example, the algorithm stops when the number of generation reaches a defined number value, or after running for a amount of time, or when the value of the fitness function for the best point in the current population is less or equal to the defined fitness function, or until the average change in the fitness function value is less than the defined value. And finally, why not, if there is no improvement in the fitness function value during a number of iterations. In our case, we used a simple stopping criteria, which is a number of iterations, and that regarding to minimize the calculation time. Okay, since we are working with a genetic algorithm, it's inevitable to talk about the fitness function. In our work, we did not deal with what we call a sub-business population, which means we don't have business processes with big or number of tasks, which lead us to assume that each business process design is linear. So we use a simple aggregation of task attributes as fitness function. And here's the main steps of the proposed approach. I will present it briefly. First, an initial population is generated randomly, then represented using the proposed representation, the task matrix. After that, some constraints are applied, as the limited size of designs, all tasks must be linked, or a task can be appear only once in a solution. After that, solutions are evaluated using the previous fitness function, and so on for a number of iterations. Okay, So for the experiments, to study and measure the performance of the genetic algorithm, which means the proposed approach, we have conducted experiments on two fronts. First one, by focusing on the right size and number of subpopulations. To get there, we use the average optimal value, AOV, and the success rate, SR, as parameters, which are taken from the job-shop shadowing problem. The second front, by focusing on the migration strategies, that we will talk about it later. So, for the first front, the figures, so the present figures, with the x-axis and y-axis represent the size, the average optimal value, and the success rate, respectively. At the beginning, the performance of the genetic algorithm is poor. The performance of the algorithm increases slowly with increase of the size. For the size equal to 200, the MPNSJ2 performance the best. But as the size continues to increase, the performance of the genetic algorithm rapidly decreases. So, to obtain an improved MPNSJ2, the value of the size should not be too small or too large. 200 would be an appropriate choice. And now let's talk about the number of subpopulations. The x and y axis represent the number of subpopulations, AOV, and the success rate, respectively. As you can see, when the number of subpopulations is equal to 5, the genetic algorithm performs the best. But as the number continues to increase, the performance of the MPNSJ2 rapidly decreases. We can conclude that a value equal or not too far than 5 will be an appropriate choice. The second front. For the second front of the experiment, we use the results obtained by the previous experiment, which means 5 subpopulations and 200 individuals by subpopulation. As you can see, we used 5 different scenarios with different task numbers, task library size, and resource numbers. Excuse me, I should have reversed the 2 columns, the resource number and the task number size. Sorry. Oh, never mind. And for the parameters of the approach, we use, as you can see, the resource obtained in the previous experiments. For the purpose of the comparison, we conducted experiments on 2 axes with 100 iterations each. First one, by diversifying the used genetic algorithm, which means we use a simple genetic algorithm, the canonical NSGA2, the a multi-population genetic algorithm, and our MPNSJ2. As second axis, we diversify the migration process. We use an adjacent migration, a neighborhood migration, then a free migration. In the figures, the axis X and Y represent the scenarios and the rate increase of non-dominated solutions compared with a simple genetic algorithm, respectively. And as you can see, the performance of the approach using our MPNSJ2 increases compared to other algorithms. Therefore, it can be concluded that the performance of the MPNSJ2 improves the results of number of non-dominated solutions, and the best couple in the proposed automated approach will be the MPNSJ2 and the free migration process. To conclude, I have presented our work dealing with business process optimization and evolutionary computing. We propose an optimization approach capable of generating non-dominated solutions with the help of a multi-population genetic algorithm. As perspective, we can take a closer look to the quality of business process. As you have seen, we use only the business function to evaluate business process design. We can also work on the relationship between the size and the number of population in the proposed algorithm. And why not working with many criteria of simulation, which means 4 criteria and more. So before finishing, I would like to remind you the title of my presentation, and I'm Nadir Mohammed from École supérieure en informatique. And thank you.